The following webinar is presented by the E-Extension Farm Energy Community of Practice at extension.org and the University of Nebraska Lincoln Extension.
I'm Jay Solomon with U of I Extension. I'm Energy and Environmental Stewardship Educator. This morning is my pleasure to introduce Dr. Alan Hansen. He's a professor in the Department of Ag and Biological Engineering at University of Illinois University of Illinois. He is the leader of the off-road equipment engineering section, which is where I had the opportunity to get to interact with Dr. Hansen. This morning, he's going to talk about biofuels. His background research is off-road machinery, systems engineering, and biofuels. Particularly working with diesel engines and tractor performance, and has moved into the biofuels and diesel engine performance and combustion area in his research recently, and has also done some things with biomass feedstock production, harvesting, and systems analysis. Nice title. One of the things that I would like to point out is it's been a pleasure having Dr. Hansen in the department for the last 16 years. Received a number of awards and accolades over the years just in being very involved. So it's glad to have an opportunity to bring him and his knowledge to this group. So with that, I will turn it over to you, Dr. Hansen.
Well, thank you, Jay. I really appreciate the introduction. And John, thank you also for helping me getting this set up and providing me guidance with what I should be talking about. I hope what I put together will be of value to the viewers, and I look forward to any questions. So the target here is to really talk more about the utilization, I think, of biodiesel. It was mentioned that maybe you already had some presentations about the sort of production side, so maybe this will be a good addition to the knowledge area in terms of biodiesel overall. So a lot of it is, how do we compare biodiesel to regular diesel fuel? What impact does it have on the engine and so on? So in order to kind of set the stage, what I've done is I just posed a whole lot of questions that I will then attempt to answer as we go along. And I'll start off with just talking about what biodiesel is, and it's probably likely that many of you will know that already, but just to make sure we're all on the same level, how is it produced very briefly. And then one of the interesting things is, of course, that we can make biodiesel from quite a lot of different feedstocks, and, that has some impacts. There's a lot of questions, well, why can't we just use straight vegetable oil in the engine? And there's some issues with that I'll talk about briefly. And then I think a big factor is, what are the key utilization issues with biodiesel that one should be thinking about out in the field? Part of that governs that obviously would be the quality standards, which are very important and provide guidance about what should the biodiesel quality be. Also, we will see that the properties of the biodiesel are somewhat affected by the feedstock, and I'll talk about some of those issues as well. And then what's going to happen in the future? What about the next generation biodiesel fuels? What do we see on the horizon coming up? And then I'll just end up with some final comments. So, right, kicking off, first of all, what is biodiesel? Well, as you probably know, it's a process of converting regular vegetable oil or animal fat to what are called monoalkyl esters through what's called a transesterification process. And the reason that we do this is to basically reduce the viscosity or the thickness of the oil, because vegetable oil is very thick, about 10 times as thick as regular diesel. Also, another benefit that comes out of doing this conversion is that you raise the cetane somewhat, the cetane number, which is a measure of the ignition quality of the fuel. And so that's an added benefit of this. And later on, we will see that even adding a little bit of biodiesel to regular diesel actually improves the lubricity of the fuel too, which is kind of a side benefit too that can be leveraged. So that's kind of how this is defined. The ASTM folks, they have some specific standards that govern the quality of the biodiesel that I'll talk about in some more detail, and I'll come to that shortly. How is it produced? I just mentioned that it's what we call a transesterification process, where you take an alcohol, typically methanol that we use here, plus a catalyst, which is typically something like caustic soda or lye, for cleaning drains. And you first of all mix the methanol and the caustic soda, and then you add it to the vegetable oil or the animal fat, and maybe a bit of heat, 50 Celsius, whatever that is in Fahrenheit. And you then mix it very vigorously, and then you let it settle out for about 8 hours, and then the glycerin layer comes out. That's a key product. The glycerin, actually, removal of that helps to reduce the viscosity quite a bit. So that's a very sort of brief, quick overview of the production process. Here in the US, a lot of the biodiesel, maybe most of the biodiesel, comes from soybean oil, and as a rough guide, we think about 1 bushel of soybeans generating about 1.5 gallons of oil, and that pretty much is a direct conversion to 1.5 gallons of biodiesel. In terms of usage in the US, it ranges quite a bit from as little as just 2% B2 in the diesel up to, of course, 100%. And there are some odd sort of percentages like B11, and this is partly driven by tax incentives in states where having it above 10% kicks in some tax incentives or tax benefits. And so that's what we see in some cases. One might question, well, only 2%, what is the value of just having 2%? Well, it turns out that 2% can really enhance the lubricity of the fuel quite a bit. And when sulfur is removed from the fuel, as it has been with diesel down to 15 parts per million, and sulfur actually is a good lubricating agent in the fuel, removing the sulfur then reduces the lubricity. If you can then add the biodiesel, even 2%, as you can see in the chart below, it can then enhance and bring back that lubricity quite dramatically and make a difference. Then there are also other percentages there, and the engine manufacturers, they will kind of have their own specifications. Typically B20 is a sort of the top limit. They're somewhat hesitant and conservative about supporting engine warranties even above 20%, even below 20%, 5 to 20, they have some concerns. But anyway, that's another story. So what is the feedstock that we can use to make biodiesel? Well, of course, we have the natural oils that can come from grains, corn oil, soybean oil, rapeseed oil, sunflower oil, etc., a whole range of different oils. Animal fats, or like lard, can be used as well. Algae is seen as a potential source of oil. And then, of course, there's a lot of waste oil out there that can be used, and that helps to reduce the overall cost of producing the fuel quite a bit. There are some issues with actually producing the biodiesel from those kind of waste oils, but which you may have already covered, I think, previously. Then, of course, there's a lot of interest in cellulosic biomass and how we could potentially convert that into some sort of biodiesel. Again, algae could be part of that, a sort of different process of doing that conversion. And we'll talk about that a little bit later on. So why not use straight vegetable oil, SVO as it's called? Well, it is. Some people are proponents on this. They think it can work. But some of the bottom line on this is that the viscosity is very high with vegetable oil, maybe as much as 10 times as much as regular diesel fuel. And that creates a lot of problems in terms of how the fuel gets atomized in the cylinder. And because of poor atomization from that high viscosity, that can then lead to the sort of coking and deposits that people talk about happening in diesel engines if you try and run vegetable oils in them. Also, the cetane number, the ignition quality is somewhat borderline with straight vegetable oil, in that it hovers in the sort of range of about 38 to 40. And the ASTM standard for regular diesel is 40, for biodiesel is 47. So it's somewhat marginal from a cetane number standpoint as well. Other things that can happen with the vegetable oil is that tests that have been done many years ago show that it could also end up in the lubricating oil and actually cause a sludge in the sump, and then you end up not having any oil being able to be pumped around the engine, and it'll seize, basically. So it has a pretty bad effect. How can it be made to work? Well, the one way to do it is to use a dual fueling system, where you can then start the engine on diesel, make sure that you warm up the engine, and then switch to, and I emphasize this, pre-warmed vegetable oil, so that then it's at the viscosity, lower viscosity similar to diesel fuel. And this has been shown to potentially work fairly well. However, the engine manufacturers, they are very conservative about, what fuels are used in the engine, especially if there are warranties involved with the engines. And so one has to be very careful about, what fuels you do run in the engines if there are engine warranties involved. In terms of utilization issues, this chart is quite a busy one, but hopefully it emphasizes some of the key utilization issues that are out there. And I'll start off with the fuel quality side, which is obviously very important. It sets the sort of baseline about the quality of the fuel, and this will impact some of the other issues that are shown here as well. US has its own standard, the Europe has its own standard as well. And actually with the US, there's an additional standard that I'll talk about. I'll go into the standards and what is measured a little bit more shortly. Moving on to the other utilization issues, oxidation stability. The stability of the vegetable oil, the biodiesel is a very key one, a very big concern for the manufacturers. The shelf life of the biodiesel is very much affected by the makeup of the biodiesel. Also within the engine, because of high temperatures, even as the biodiesel is being fed into the engine, even as a blend with diesel, it's possible that deposits can form in, for instance, an injector and in parts of the pumping system, and that obviously inhibits the operation and it affects the durability of the engine. And you get then these deposits that do that. Also, there can be some issues with maybe corrosion as well in the fuel injection system. So oxidation stability remains a big factor, and we'll talk about that some more. Fuel foaming, as mentioned, is a little bit where as you're filling up the tank, it may foam quite a bit. There are anti-foam agents that help with that. Then compatibility with new engines is a very big issue. How compatible is biodiesel when you burn it with the new after-treatment systems, for instance? How does it affect the catalyst in the after-treatment system? Also the particulate filter performance. Because when you burn biodiesel in the engine, you can end up with different exhaust temperatures, for instance. So your warm-up can affect your particulate filter in terms of regeneration, and so these factors that come into play when you introduce biodiesel, which has a different set of exhaust products compared to regular diesel. Another one is water in the fuel, and I think this has been mentioned that, for instance, the growth of algae in the fuel, which happens with regular diesel, when you have water and diesel, at that interface between the water and the diesel, it's possible that you get a sort of an algae growth that then ends up blocking the filters. And then the thing is with biodiesel, it likes to absorb the water, and so it may then exacerbate that problem of the growth of that bacteria or that algae. Also, the water can impact on the fuel injection system, that you may get corrosion because of the water, so that's a potential side effect that's not good. And then finally, a really important factor, especially in cold climate countries and where we are located here in Illinois and Nebraska, and where some of you are probably from, the cold flow aspect is very important. So if the temperature gets pretty low, the fuel will start to gel, and you will then, the fuel will cease to flow into the fuel pump and engine will stop. So this is a big factor that comes into play as well. I'm going to talk very briefly about the standards, and this is a very busy slide with many different standards, but the purpose of this is just to show you the extent of the standard and what properties are really monitored and have to be looked at when you're looking at the standards. So they can vary from, what is the residual amount of methanol in there, the flash point, the safety of the fuel, the flammability of the fuel, how much water there is in there, the viscosity, ash, C10 number, we mentioned that already, the Clyde point, that's what we talk about, the gelling of the fuel, and then some residuals from the production process as well, how much glycerin is there that may have been left over from the production process. Phosphorus is very important as well. And then right at the bottom, oxidation stability, there's a measure to determine that as well. So just to look at some of these in more detail, for instance, the methanol and the flash point. So the methanol flash point aspect is related to safety, because any residual methanol in the fuel increases the flammability potential of the fuel. And so whereas we think about regular diesel being relatively safe from a flammability standpoint, and biodiesel potentially can even be safer, if there's any residual methanol in that biodiesel, it then has a big impact on the flammability. It raises the flammability, and some biodiesel manufacturing facilities have had big fires because of this. Viscosity. So this impacts on the atomization of the fuel in the combustion chamber, so it affects combustion quite a bit, and hence there's a particular maximum limit, but it actually turns out to be a little bit higher for biodiesel relative to diesel. Cetane number also impacts on combustion, it impacts on the emissions. Cetane number kind of relates to what we call the ignition delay. So once you inject the fuel, how long does it take before you get combustion actually beginning? And the lower the cetane number, the longer that delay, which then impacts on, as I said, the emissions and the performance of the engine. Cloud point and the cold filter plugging point relate to the ability of the fuel to flow under cold conditions. So this is a very important issue, particularly in our part of the country. May not be so much of an issue in warmer climates. And a lot of these properties, as you will see down below, are affected by the feedstock itself and the storage of the fuel. Others, oxidative stability, I mentioned how important that is right up at the front. This is really a measure of the resistance of the fuel to deterioration while it's stored, or what happens within the engine. Acid number, this is another one that relates again to engine deposits, corrosion, and it's also what we say is a measure of the free fatty acids in the fuel, which is bad. Free and total glycerol that comes from the production process, the sort of byproducts if the fuel hasn't been cleaned properly, and these can be contaminants in the fuel that are not good. And then finally, metals and phosphorus. Okay, so these are the factors that impact on the emissions after treatment systems. They can then poison the catalyst and affect the overall after treatment system performance. So next question is, how are the properties of the biodiesel affected by the feedstock, whether we make it from sunflower oil or soybean oil or rapeseed oil, as it is made a lot in Europe? Well, when you look at these various oils or fats, they consist of fatty acids, okay? And you get so-called saturated fatty acids, meaning that there are no double bonds within the chain of that particular acid. And then you get the so-called monounsaturated acids that have one double bond, and then polyunsaturates, multiple double bonds. And so, as in health, we talk about saturated fats are bad for health. Well, how does it impact the engine, health of the engine? Same with monounsaturates, polyunsaturates. So here you can see the typical profile, for instance, with soybeans. So saturated fats tend to be on the lower side. The oleic acid, the C18-1, that's C18 means that it's 18 a chain length for the molecule of 18 carbon atoms with one double bond, and then you've got the linoleic acid, polyunsaturates, and the linolenic acid as well there. And so with soybeans, you tend to get a fair amount of C18-2, followed by C18-1, but it depends also on the variety of the soybeans. You get high oleic acid soybeans, and obviously the high oleic acid component is pretty high. So the question is, well, how does this affect the engine, the makeup of the fatty acids there? Well, if we look at other oils, it's across the map. They can vary a great deal depending on the oil itself. Palm oil, you'll have a lot of palmitic acid, which I believe is C16. Other oils may have larger amounts of other types of acid. So it varies quite a lot depending on the oil source there. So how does it impact on the engine? Well, if you look at the cetane number, it turns out that the saturated fats are really good for increasing the cetane number. As you can see here, C16, C18, they really boost the cetane number a lot, remembering that the limit is about 40 for regular diesel, 47 for biodiesel. But when we get to the unsaturated components, then the cetane number comes down pretty dramatically as we're going from oleic, then oleic, as we add the number of double bonds to the acid, to the oil. When we look at the emission side of things, so here's a chart that kind of shows the non-road emission standards, the tier standards in the US, and how they impact on the particulate emissions and the NOx emissions, which are the two key emissions for diesel engines. And you can see how the emissions have narrowed down over the years, and right now we are in tier 4, that little block right in the bottom left corner of the graph. So we've had this huge reduction in the tier 3 to tier 2 to tier 1, 90% actually reduction there, so huge reduction. So the thing is for the engine manufacturer, the challenges of getting the fuels to be producing that little bit of emissions. So how does the makeup of the oil impact on those emissions? Well, this is a relatively old chart that was put together in 1998, where some tests were done on a specific engine at that time. And you can see there that it turns out that the saturated fats help to reduce the emissions, both particulate and NOx emissions, simultaneously. And that's always the challenge of getting a reduction of both of those simultaneously. So you can see then that the fatty acid makeup does impact on the emissions as well. So overall, what is interesting here is to sort of compare the health versus fuel effects, of the fatty acids. And this is my attempt to illustrate, the impact on cholesterol. We kind of know that from a health standpoint, that, the saturated fats are really bad for health. But as we move to the right, to the monounsaturates, polyunsaturates, we get more and more positive impacts on health. From an engine standpoint, as we saw earlier, the cetane number is improved with the saturated fats as the length of the chain increases. But as we get into the unsaturated part, it gets worse. What about the oxidative stability? Well, it turns out that the saturated fats are really good because you don't have those double bonds that are susceptible to oxidation in the fuel. But as you get more undouble bonds, then your oxidative stability goes down pretty dramatically. On the cold weather side, it turns out then with the saturated fats that you have some problems, okay? As you increase the chain length, then the cold weather issue increases. But with the unsaturated components, as you increase the amount of unsaturation, then the cold weather temperature drops, it gets better there. So you've got these factors that come into play. It ends up almost being a compromise between these different types of properties. The oxidation stability issue, as I mentioned, is a very big one. It has received a lot of attention, how to set up tests and standards, and we have what is called the Rancimat test that's included in the Europe test, also in the ASTM test, certain number of hours where you have this, you subject the oil to a certain temperature and then look at its degradation. So this is a big factor that has been getting a lot of attention over time. What causes the low stability? Like I've already mentioned, the unsaturation of fatty acids is a very big one. Even the feedstock, if it's new versus recycled, can have an impact. If you're going to be using waste oil, it can have an impact. It turns out that some oils have natural antioxidants in them, which then can help the degradation. Typically, animal fats that are used for biodiesel have no antioxidants, so they may be more susceptible to oxidation. In terms of the production side of things, the distillation process may also affect the stability of the fuel. And then, of course, how you handle the fuel can be very important, how much you expose it to air, temperatures, all that kind of thing. What about additives? So there are additives that can increase the stability, and a number of people have done tests on these, and some antioxidants can be added that can have a big effect. They can cost a fair amount of money, so that adds to the cost of the fuel. The fuel can age over time pretty dramatically, as you can see in the bottom left side there. So just letting the fuel stand, it will naturally degrade over time as well. So that's a big issue. In cold weather, so the fuels have a big problem potentially. Even soybean derived biodiesel can be starting to plug, to freeze, close to zero. Rapeseed, not so bad. Palm oil is really bad. Tallow from animal fat, pretty bad. So these are issues that can come up with the use of the oil. There are improvers or additives that, again, can help with these. Some of them are matched to the biodiesel. For instance, some will work for rapeseed methyl esters in Europe, but not necessarily good for soybean methyl esters. So these are some issues that can come up with the additives as well there. I should just mention one thing that's important is, when you're running biodiesel out there in the field, there are questions about, well, how does it impact on the power from the engine? This is pretty important. And actually, the difference between straight biodiesel and regular diesel is not that great. There may be about a 10 to 15% drop, if you use B100. In terms of blends, if you have 2 to 5% biodiesel in the diesel, it's going to have absolutely very little impact on the power that the engine produces in the end. So it is affected by the amount of biodiesel in the diesel, but overall, one can perhaps expect not a very big hit in terms of the power generated from the engine as you might add more biodiesel. What about emissions? So this is really interesting. With biodiesel, you will expect a natural benefit because of the oxygen that's bound in the biodiesel, which then helps in the combustion process. Because now when you have biodiesel going into the cylinder, that oxygen bound in the biodiesel contributes to a much cleaner burning of the fuel. So you will then naturally see a reduction in carbon monoxide, particulates, any unburnt hydrocarbons because of that oxygen bound in the fuel. The big question always is the NOx emissions. So NOx emissions, oxides of nitrogen, are generated because of high temperatures that are generated in the combustion chamber. So the higher the temperatures, the more likely the nitrogen will be oxidized in the chamber. So engine manufacturers are always looking at ways to try and limit that high temperature to ensure that the NOx generated is not too high. So a lot of tests that were done initially on biodiesel kind of showed maybe an increase in NOx emissions, as you can see in the little chart on the right-hand side there, even maybe as much as 10%. But subsequently, tests have been done by the folks in the different laboratories, DOE laboratories, and they found a lot of variation from one engine to the next. Some engines, maybe even less NOx emissions with biodiesel. So it very much depends on the engine. The injection system can have a big effect overall as well. So the jury is kind of out on whether it's actually true that the NOx emissions are increased with biodiesel. So what about next generation biodiesel fuels? Well, when we look at the alcohols, there's been a lot of interest in saying, well, what can we add to diesel fuel to extend the supply? Even ethanol has been looked at being added to diesel fuel, and I think and I've worked with some of this myself, ethanol is really much more suited to gasoline combustion than diesel combustion. In order to make it work in a diesel engine, you have to have a very good additive that turns around all the issues, improving the cetane number, improving the lubricity, making it burn properly, making sure it doesn't separate out from the diesel, all those issues. But when you go to the higher alcohols like butanol, there is actually seems to be a lot of potential attraction in terms of a better compatibility of the biobutanol with diesel combustion. In fact, it's almost a sort of in-between, where you could potentially use it in gasoline engines, or you could use it in diesel engines. So there's quite a lot of research actually taking place. In fact, even my colleagues in mechanical engineering and myself, we have an NSF grant looking at biobutanol being used in diesel engines. And so it's showing some really interesting characteristics. You may have probably heard of the so-called drop-in fuels that are being looked at and starting to be even provided, especially in Europe. These are fuels that can be manufactured, and they resemble, regular gasoline or diesel fuels in in terms of their makeup. And so that's why they're called drop-in fuels. They can just immediately replace regular diesel or regular gasoline and be used in existing infrastructures without any sort of side effects because of that. There is a lot of talk about so-called, what we call XTL, X to liquid, or, liquid to liquid or gas to liquid processes. In Europe, this is pretty big. Also, vegetable oils that can be so-called hydrotreated, where you actually deliberately have a reaction to add hydrogen to the oils to make them saturated, for instance, improve the Cetane number. There are also other different conversion processes, biomass to liquid, where you use gasification or pyrolysis or hydrothermal liquefaction, and then be able to generate fuels that resemble diesel fuel or gasoline. So there's a lot of interest in those as well. In these production processes, like I mentioned, then you then generate these carbon-based feedstocks that then resemble regular diesel or gasoline. Talking about about engines, and so one of the things that's really of great interest is there's a lot of research going on in the space between gasoline and diesel technologies. So what we call homogeneous charge compression ignition, where you are relying on processes taking place in the combustion chamber that are in a way similar to both gasoline and diesel. Okay, so how is it similar to gasoline? Well, you have a homogeneous charge that you start off. Your air and fuel is pre-mixed, okay? But you're not using a spark to ignite it. You're using just the high compression to have the fuel self-ignite. And so you then sort of, in a sense, combining the benefits of both gasoline and diesel to then have the combustion take place. And so some of the interest is, well, how do biofuels impact on how well fuels might burn in this space? And so there's interest in that area quite a bit at the moment. So what are the technology requirements, and why are they different from regular in terms of engines? How is it different? So how can we maybe leverage the unique properties of biofuels to make engines run better? So as I mentioned, most biofuels have oxygen bound in the molecule, and this has a really big impact on the emission side of things. It helps to lower a lot of the emissions that we see taking place with regular diesel, lower soot or particulates, lower carbon monoxide, as I showed you earlier. Also, potentially, one of the things of value is that the molecules or the makeup of the fuel is less complicated. For instance, with ethanol, you have one single chemical component. Even with biodiesel, you have a finite number of fatty acids that make up the oil. So in a sense, it's easier to control the quality because of that, that you have a less complicated fuel, because regular diesel, regular gasoline comprises, many, even hundreds, thousands of hydrocarbons. So the quality control is a lot more difficult in those fuels. So maybe that's a benefit of biofuels. So what about the future? So, algae is receiving a lot of attention now as a potential feedstock. Part of the reason for that is that you can have a really small footprint area in which to produce the algae, and then it grows very quickly, and you can then generate what we call the lipids, the fatty acids, very quickly from that. So, and it has many other potential sort of co-products that can be of value. Challenges are the production. There are quite a few challenges with it in order to produce the algae. Some of these, first of all, the cultivation of the algae is a big factor. How do you then, how do you harvest the algae? How do you then do the extraction of the things that are useful in the algae, and then make sure that they are able to generate the fuels with the right sort of properties also come up from that. So some final comments. I think the quality of the biodiesel remains a big issue, and John mentioned, that especially if folks are wanting to produce biodiesel, at home in a sort of local sort of mode, how do you control the quality or determine that your biodiesel is clean enough? can be a big issue. What we can expect, though, in the future is, petroleum is going to be around for quite a while, even though I think there will be more biofuel produced in the future because of emissions issues. One big factor about biofuels is as soon as you start to use them in engines, you have an immediate impact on greenhouse gas emissions, because when you're growing the crops to generate the biofuels, you're taking CO2 out of the atmosphere. And then obviously when you burn the biofuel, you are releasing that CO2, but hopefully there's a neutral effect from that. Another factor is, as I mentioned, also climate change. Trying to reduce the CO2 may provide a greater sort of emphasis on the value of renewable fuels like biodiesel. But another factor I think that's combined with that is to ensure that we have better efficiency of using the energy. And I think this is incorporated in standards and that kind of thing that are coming out. EPA, you've probably seen, are starting to look at CO2 sort of standards as well. And we may see that pretty soon coming into effect.
This webinar has been brought to you by the Farm Energy Community of Practice and the University of Nebraska-Lincoln Extension. For more information, go to farmenergymedia.extension.org.